So we're going to talk a little bit about what a continuous function is. Now when you think of the word continuous, I want you to tell me what comes to mind.
Forever.
Forever. What else?
Not stopping.
It doesn't stop. That's exactly right. So that's what we need to think about when we think about a continuous function. It is a graph which has no breaks, no holes, or no gaps. So when we think of a continuous function, we think of a function that we can take our pen and we can draw it and we never have to pick our pen up. Okay, that is what a continuous function is. And so, along with the continuous function is what is known as the concept of a limit. A limit is one of the fundamental ideas in calculus. Okay, and so you're going to get an introduction now. We won't spend a lot of time on limits, but you're just going to kind of get that brief introduction so that if you ever have to take calculus, okay, you'll at least have that in your mind and you'll have somewhere to start with. Okay, but a limit is a concept of approaching a value without necessarily ever reaching it. Okay, it's a concept of approaching a value without necessarily ever reaching it. And this is how a limit is written mathematically. And what is written down here below is how this is read. Okay, so this is read as the limit, that's what the LAM stands for, of f of x, this function right here, as x approaches c, right here, is L. Okay, so that's how you start by reading it. The limit, okay, of f of x as x approaches c is L. And so an example of what a limit would look like is it might be this. The limit of x plus 2 as x approaches 4 is 6. So basically we're subbing things in, but that would be an example of how one is written. But like I said, this is just kind of a brief introduction, and for those of you who take calculus, we'll spend a whole chapter on limits. So now we've talked kind of about continuous functions. We're now going to talk about discontinuous functions. So when you think about a discontinuous function with the analogy about the pen, what would a discontinuous function be? Okay, so if I've got my pen or pencil, what am I going to have to do with that pen or pencil? Pick it up. All right, so a discontinuous function is a function that has a hole, a break, or a gap. And so we classify those holes, breaks, or gaps. And so if you look here, okay, this is what you need to write down, okay, in this chart. Let's kind of disseminate and get some of the crucial information. Okay, this is what I would do. I would draw a picture of the graph. On this one, I would draw a picture of the graph. And then I would label those as non-removable discontinuities. Then when you're done with that, I would draw a picture of this graph, and notice this is a removable discontinuity. So you have non-removable, removable. You don't need to know about infinite or jump discontinuities. Okay? If you take a class in the future that deals with these, you can pick it up there. But for right now, we're going to focus on the non-removable and the removable discontinuities. Now, there's a really easy way, okay, to determine if it's removable or non-removable. Really easy, and I'm going to show that to you after you get this done. So when I think of the word remove, what does that mean? Take away. So using my pen, is there a way I could place one dot and take away this hole in the graph? And make it so that it was continuous. So on this blue graph right here, is there a way I could take my pen, put a dot, and then the graph is, or the hole is removed?
Yes, when it's open.
Yeah. There, I put a dot in there, right? So now if you look at the graph, are there any breaks in the graph? No, the graph continues. I could take my pen and I could draw straight up that line and it works. So that's why we call that one a removable discontinuity, because with one dot you can remove that hole. Now the other two, what do you notice? Can't do that. So, just a second. Okay, so if I look at that first one, if I put one dot, can I remove that discontinuity so that there won't be a break? So if I put a dot here, have I removed that discontinuity? No, it's still got a hole, it's still got a gap. So if I put a dot here, like right here, can I remove that discontinuity? No, there's still a gap in the graph. So that's how you distinguish between a non-removable and removable. If you can take one dot and get rid of it. Graphing calculators, let's go. Get them out. I need you to graph f of x equals 2x squared minus 3x minus 1. So graph, so we go to y equals, you are going to graph 2x squared. So when you get that graph, I want you to think about what the shape of the graph looks like. What does it look like? What's that called? I know, what's that called? Parabola. It's parabola. Okay? And so we're looking specifically at x equals 2. So you see your x equals 2. Is the graph continuous there? Now when I say continuous, that means there's no holes. Are there any holes on the graph? No, so this graph is continuous. So is it continuous?
Yes.
Yes.
That's your answer.
That's your answer.
We're gonna write these.
You're going to use your graphing calculator a lot. All right, let's look at this one. X cubed. So is x cubed continuous at x equals 0? Yes. Okay, so yes. And in fact, what do you know about that whole function?
It is
Well, yeah, okay, specifically about continuity, what do you know about the whole function? It's continuous everywhere, right? There's no holes or breaks. Okay, let's look at this one. Now this is called a piecewise function. Now when I say piecewise, I mean P-I-E-C-E. So a piece of one and a piece of another. And so we're going to graph these by hand.
I don't think this has.
Can't do this one on the graphing calculator. Okay. Now our key point here is 0. Why is it 0? Because of this right here. So 0 is your starting point. So on this first one, I'm going to start at 0. Now this says less than 0. Okay? So what would be a value less than 0? -1 and then -2. So I'm going to plug those values in. So at 0, if I plug it in here, what do I get? I get 1 divided by 0, which is what? Okay, 1 divided by 0, what'd you say? Undefined. Okay, so we'll talk a little bit about what that means. What's 1 divided by -1? -1, and what's 1 divided by 2? Or -2, sorry. -0.5. Okay? So I'm going to start by plotting. At -2, I'm going to plot -0.5. At -1, I'm going to plot -1. At 0, it's undefined. Whenever you have an undefined function, what that means, okay, is that means that there's an asymptote, or that means there's just a line there. And so how we symbolize that undefined or the asymptote, if you look, I start here at -0.5, -1. Where do you think another value would be? Maybe like right here. Would that be somewhere below? Okay, so this is actually what that graph is going to look like. Now, it can't touch 0. Okay? Can't touch 0. So then now, I'm going to start with this next statement. X is greater than or equal to 0. So I'm going to start with 0 again. Okay, but look at what it says. It says greater than 0. So what values do you think you'll use it now? 1 and 2. Very good. So if I plug 0 in, what do I get? 0. If I plug 1 in, what do I get? If I plug 2 in, what do I get? 2. Okay. So now this says I've got a point at 0, 0. So now whenever you do these piecewise functions, we're going to talk about doing an open circle at this key point. Not yet, because this says greater than or equal to 0. So whenever it says that equal to, it means you include the point.
Yeah.
If it would have just had greater than 0, you would have put an open circle there. Okay, 1, 1. There's your point. 2, 2. There's your point. And so what you're going to do is start at 0, and you're going to angle this line off. And that is what the piecewise function looks like. Okay, the open circle only occurs at 0, and see, since there wasn't a point here on the blue, don't have to worry about it. Okay, so I want you to think about this. What type of discontinuity is there at 0? At 0, what type of discontinuity is that? You have two options. Okay, perfect. Say it louder.
Non-removable.
Okay, there you go. Okay, it's a non-removable discontinuity because remember, you can't get rid of that with a dot. It's either non-removable or removable. Okay. So let's look at this next statement. It says determine whether each function is continuous at the given x values. If it's discontinuous, identify the type of discontinuity as either removable or non-removable. Now, there's one thing that I hope you're understanding how to enter on your calculator, and I hope you did today. This is how you have to enter fractions in. You have to do parentheses around the whole thing. And so there was one that had like x plus 2 on the top and x plus 1 on the bottom. You needed to put parentheses around each of those. Okay, so let's go ahead and graph this and see what you get. So 1, and then you're just going to put the division sign, and then parentheses x minus 1, and then right parentheses. Yes. You're going to see something that looks a little funky.
I know we have to graph it.
No, you don't have to graph it, but you have to graph it on your graphing calculator. So tell me what you see. This is my key point, right? Okay, what does the graph do to the left of 1? Goes like this. What does the graph do to the right of 1? Goes like this. We call 1 an asymptote. And when we're graphing them, we usually symbolize asymptotes with a dashed line. What that means, and what I usually think of an asymptote is I think of it as an electric fence. Okay? Why do you think of it as an electric fence? Because the graph gets as close and close and close to it as it can, but if it touches it, it gets zapped. Okay? So, it's an invisible boundary. The graph gets close and close and close, but it never, ever touches it. That's what an asymptote is. And so in looking at this, first of all, is this discontinuous at 1? Yep. It's got a hole in the graph. Is it removable or non-removable? Can I remove it with 1 dot? So then it is a non-removable. So is it discontinuous? Yes, and it is non-removable. Pretty straightforward. Let's try another one. Okay, so this one you have to be careful how you enter it in. We'll probably call this our last one today. X plus 3 divided by x squared minus 9. This is how you have to enter it in. X plus 3 divided by x squared minus 9. What? We'll get to that. Graph it and then you'll see why. Now, I want you, once you enter it in, I want you to go to Zoom. If you already went to Graph, that's fine. I want you to go to Zoom, which is in the top middle, and I want you to change the screen to Z decimal, which is number 4. Remember, we were in Z standard, but I want you to go to Z decimal because you'll see something a little funny. Now, we're looking for discontinuities. So the first one is at x equals 3. Is there a discontinuity at x equals 3?
No.
X equals 3. What do you notice about it x equals 3? Okay, at x equals 3, this is what I notice happens. Didn't that happen? So at 3, you have an, what was that called? What was that thing called I just said? Asymptote. So it is discontinuous. And what type of discontinuity is it? Non-removable, good. No, it doesn't. I know it does here, but it's actually not. It's actually like right like this. Okay, now we're going to look at negative 3. Now in your window, what do you notice at negative 3? At negative 3, yeah, it's a little below. Do you notice anything else? It's what? It's got a little gap. So what do you think is there? A hole, yep, a circle. So actually at negative 3, I'll scoot out here. At negative 3, and that's why we changed it to the Z decimal window, because at negative 3 what ends up happening is you get a little gap in your graph that looks like that. And this is actually what it is. It's a little hole in the graph. Okay. Is that discontinuous or continuous? Discontinuous, what kind is it called? Yes, good, removable. Okay. So, I think we got a good start on today. And so what I'm going to go ahead and do is jump to your homework. And we'll talk about end behavior tomorrow. If you want to just write down the whole thing, that would be great. What can you do? You can do 2 through 10 to evens. So you can do the first 5. Okay, actually, I'm going to make a change. There we go. Okay, so you should be able to do the first 5, the 2 through 10 to evens. And I would actually highly recommend that you even get going on it now and try and get that done because tomorrow we're going to talk about something a little different. So.